Having examined the concept of pressure being transmitted through an incompressible liquid to do useful work, we will now go on to consider the case of pressure being applied to a compressible gas. This image shows a bicycle pump, which is used to pump air into bicycle tyres. To begin our examination of applying pressure to gases, we will seal off the small hole at the end of the pump and compress the air inside by pushing down on the plunger. You've probably done this for yourself many times. But before any force is applied to the plunger, the pressure inside and outside the pump is atmospheric pressure. When the plunger is pressed down, it squeezes the air inside the pump chamber, compressing the air molecules and raising the pressure of the air in the chamber. As we have said, gas, unlike liquid, is compressible. So, whereas the volume occupied by a liquid does not change when pressure is applied to it, the volume occupied by the air in the chamber of the pump reduces as the plunger is depressed and the air pressure in the chamber rises. Then, when the plunger is released, only atmospheric pressure is now acting on the outside of the plunger piston, the force used to depress the piston having been removed. The pressure of the air inside the pump chamber is now, however, higher than atmospheric. The air in the chamber is therefore applying a greater force to the piston of the plunger than the atmospheric air on the other side of the piston. So when the plunger is released, the air in the pump chamber returns to its original volume and pressure, that is, atmospheric pressure. Let's look at what's happening a little more closely from the points of view of work and energy. When the plunger is pushed in, we see that a force moves through a distance, so work is done in compressing the air in the pump chamber. Obviously, energy is expended to do that work. But with this pump, unlike the hydraulic machine we were considering earlier, there is no actual work output. So where does the energy go to which is used to compress the gas? We know that it cannot disappear. Well, as the air in the chamber is compressed by the piston of the plunger, the temperature of the gas rises. We see then that the energy used to compress the gas has been converted into heat energy. If you yourself have ever pumped up a bicycle tyre using this type of pump, you will have noticed that the end of the pump linked to the tyre by the adapter gets hot. If you try for yourself the bicycle pump experiment you've been looking at here, you may notice that the plunger, when it is released, does not always return to its exact original position. You may see that often it moves a little further out compared to its original position. So what might be going on here? When the plunger of the pump compresses the air inside the pump chamber, it raises the temperature of the air inside the chamber. This increase in temperature is accompanied by a further increase in the pressure exerted by the air inside the chamber. This further increase in air pressure inside the chamber means that the pump handle, when it is released, is pushed further out than its original uncompressed position. The observations that we have made in this consideration of the action of a simple bicycle pump show us that there is a close relationship between the pressure, volume, and temperature of a gas. We will now go on to look at the physical laws which explain this relationship. These are often referred to as the gas laws. This further increase in pressure means that the pump handle, when it is released, is pushed further out than its original uncompressed position.